Okay. N-step learning, N-step TD learning can be pretty effective in allowing us to balance the bias and variance trade-off. However, it is still, as long as we're not using the one-step TD learning, it's still an on-policy algorithm, right? And as we said before, we'd like to steer away as much as possible from on-policy algorithms because they are highly sensitive to the policy that we're using to actually interact with the environment. Meaning that as our policy evolves over time, we have to discard of old samples, which is not sample efficient, right? It's not very efficient. And so the question is, can we perform off-policy N-step TD learning? That is, can we do something in order to change our N-step TD learning approaches, for instance, N-step SARSA, as we just saw, to learn off policy, to learn a target policy that is different than the behavioral policy, than the policy that we're using to interact with the environment or to draw our samples from. Any idea? Can we?
Well, previously we saw that's possible using importance sampling.
That's a good idea, yeah, that's true. So we previously saw that we can actually use Monte Carlo approach, and make that off policy by using importance sampling, the importance sampling ratio, importance sampling methods. So we can do the same with N-step TD learning. Of course, N-step TD learning in the extreme is just a Monte Carlo approach. So as a reminder, in importance sampling, what we're trying to do is to define the probability for sampling a specific trajectory that we actually saw in the environment. What is we try to compute or to define the probability of seeing that trajectory under our behavioral policy. And you might say, what do you mean? We just sampled it from the behavioral policy, so isn't that just one? Sometimes, if your behavioral policy is deterministic, first of all, and secondly, if you don't have noise in the environment, noisy transition probabilities. But not necessarily the case, right? And actually, in the pseudocode that we've seen previously for Monte Carlo plus importance sampling, we specifically chose a behavioral policy that is deterministic because it reduces some of the bookkeeping that we need to perform. And with respect to the transition probabilities, they get cancelled out, so that's not important. So I can just say, this probability, the probability of sampling a specific trajectory with a behavioral policy, can be practically 1 in some cases if we set it up correctly, but not necessarily. We can also use this a very similar definition to define the probability of sampling that trajectory from the target policy that we're trying to learn for. And then we can define the importance sampling ratio as the difference or the ratio in these probabilities. And we can actually compute that ratio without assuming to know the model, without assuming to know the transition probabilities, right? These pi. Because they cancel out in the importance sampling ratio, in the IS ratio. Once we have this importance sampling ratio, we saw that we can perform off-policy learning, right? It might be not very efficient. We saw that before because of this importance sampling ratio can have some pretty weird or extreme values. And so we saw how to normalize these values, the trick that helps with that. But in essence, this results in unbiased off-policy learning. Okay, and so now we can define N-step SARSA plus importance sampling, right, for off-policy learning, for off-policy N-step learning. This further a bit complicates the pseudocode, so we won't do that to you again, so this is similar to on-policy N-step SARSA. The observed N-step return is now multiplied by the importance sampling ratio, right? We have to have some extra bookkeeping in order to make this off-policy by adding the importance sampling ratio. This can be used for learning Q star while following a different policy, a behavioral policy, for instance, soft epsilon greedy exploration. When we attempt to learn Q star values with n-step search or plus important sampling, how should we define the target policy? Any idea? The target policy. So I'm trying to learn Q star, meaning I'm trying to eventually perform optimally. So what should be my target policy? And I'm learning Q values, hopefully Q star values along
your maximum Q value in each state.
Your argument, the action that maximizes the Q value, right? So that's the difference between argmax or the max. Right, so if we are trying to converge our target policy is the one that that maximizes the Q star values, or we're trying to converge on the Q star values, so our target policy should be the optimal policy, right? So we can easily define that as the argmax, the action that maximizes the Q value as we converge toward Q star. This will be pi star, right? It will become pi star. How should we define the behavior policy?
Since it's off policy, can it be anything?
Yes, it can be anything with a caveat.
That it's the maximum of the current Q value?
That we have
argmax?
Sufficient exploration, right. So in order to converge on the correct Q values, we must guarantee that we have sufficient exploration, infinitely often visitation for every state in action pair. So any policy that provides coverage, not only coverage actually, coverage and sufficient exploration and infinitely often visitation. Okay? It's not always the same. Coverage does not always imply infinite often visitation. But actually it does over time. So we define coverage as just a probability of visiting each state action pair. If you continue using the same policy that guarantees coverage, then you should be fine.